So here we are in chapter 2. This is our second part, beginning to talk about binary arithmetic. So in this section, we're going to look at the basic integer operations of binary arithmetic, so addition, subtraction, multiplication, and division, the rules of binary arithmetic, which are identical to the rules of decimal arithmetic, so it's not like I'm teaching you any kind of new math. And really, the only difference is that decimal arithmetic uses it in a base 10 and has 10 digit, whereas binary arithmetic uses the base 2 and has 2 digits. So the addition, subtraction, multiplication tables for binary arithmetic are given in our figure. And it's a much simpler set, right, than our decimal counterparts because we're only working with our 2 digits. So we can see in addition, right, we add 2 zeros together and we get 0, 0 and 1 and we get 1. Same for subtraction. Multiplication follows the same rules. You can't multiply something by 0 without getting 0. And then we can see here on the far right side, the addition with 3 bits helps you kind of see how to understand when we carry a bit. So while these tables here define what happens when you add, subtract, or multiply two single-bit binary values, real computers use 8, 16, right, 32, or 64-bit numbers. And when we start working with our binary words, then it gets a little more complex. So let's take a look at this example. We can see that adding or subtracting 2 bits may carry or borrow just like in decimal arithmetic. So here we can see when we add 2 binary words, we add pairs of bits, a column at a time, starting with the least significant bit, and then any carryout has to be added to the next column on the left, right? So least significant starting on the right, moving leftwards. So let's take a look at these 2 examples. So on our first one, when we add together our ones, our ones, our ones, right? And you can follow it over as we move to the right, or I'm sorry, to the left. Right, same for these other ones where we're adding. And then when we subtract, we can take a look at these examples here. We have to remember that 0 minus 1 results in a difference of 1, and we have to borrow from the column on the left. And you can end up with negatives. We see here in example 5. And then when we multiply, right, when you learned decimal multiplication, you had to memorize tables from 1 times 1 equals 1 to 9 times 9 equals 81. But in binary multiplication, this is much easier because we just have this simple multiplication table that multiplies 2 bits to get a single bit product. So same rules apply. If we multiply by 0, we get a 0. And if we multiply 1 times 1, we get 1. So let's take a look at an example that demonstrates the multiplication of a binary word. So we can see we have our word 0, 1, 1, 0, 1, 0, 0, 1, right? Our notation of 2. And then we have our multiplier, 0, 1, 0, 0, 1, 0, 0, 1. And so we can take a look at the product of 2 n-bit words is a 2 to the n-bit word. Or I'm sorry, 2 n-bit word. I said that funny. So we start with the least significant bit of the multiplier and test whether it's a 1 or a 0. If it's a 0, we write down n zeros, and if it's a 1, we write down the multiplier, right? We call this a partial product. You can then test the next bit of the multiplicand to the left, carry out the same operation. In this case, you write 0 or the multiplier 1 place to the left, and our partial product is shifted left. The process is continued until you've examined each bit in turn. And we can see this operation walked through in the table. And at the end, our last step, we add together the in partial products to generate the product of the multiplier and the multiplicand. Now this is for humans. Computers do not perform multiplication the way that we do. We will look at some of the ways in which computers mechanize multiplication, but ultimately, this is the way that humans would understand it and perform this kind of operation. So before we go further, we need to talk a little bit about some vital concepts in computer arithmetic. When we process text, we expect the computer to get it right. Right? We expect computers to process text accurately. We would be surprised if the computer suddenly started spontaneously spelling words incorrectly or suddenly started getting the math wrong, right? But numerical errors can be introduced into calculations for a couple of reasons. The first cause is an error in the property of the numbers themselves, and the second is the inability to carry out arithmetic operations exactly. Right? And we have a couple of different terms to learn that talk about these different types of errors and so that you can differentiate between them. So the first one is range, which is the variation between the largest and smallest value that can be represented by a number, right? That's the measure of its range. So a natural binary number has a range of 0 to 2 to the n minus 1, right? A 2's complement signed integer in n bits can represent numbers in the range of negative 2 to the n minus 1 to positive 2 to the n minus 1 minus 1. So this gets even more complicated when we start talking about floating point real numbers that use scientific notation. That's a little out of the scope of what we're going to discuss in this class and is a much more advanced computer architecture topic. Precision is of a number, right? The precision of a number is the measure of how well we can represent it. So pi is a great example, as we cannot exactly represent pi in a binary or in a decimal real number. No matter how many bits we take, if we use 5 decimal digits to represent pi, we can say its precision is 1 in 10 to the 5th. If we take 20 digits, we can represent it to 1 part in 10 to the 20th. So a lot of times we talk about precision in terms of decimal places, right? So when we want to talk about the number of decimal places to the right-hand side, you may be talking about a specific amount of precision. Some different languages have different types of floating point numbers that have different types of precision, and you would use each one under specific cases where you needed more or less accurate precision. Then we have accuracy, which is the difference between the representation of the number and its actual value. So this example here, if we measure the temperature of liquid as 51.32 and its actual temperature is 51.34, then the accuracy would be 0.02. It's tempting to confuse accuracy and precision, but they are definitely not the same. So in our example, the temperature of the liquid may be measured as 51.32000001, which is a precision of 8 significant figures. But if its actual temperature is 51.34, the accuracy is only to 3 significant figures. So understanding the difference between precision and accuracy and that they are 2 different things and how to express that. Then we have errors. An error is really just a measure of accuracy. So if we have a situation where like an error equals true kind of value with an actual value, then what matters to us as like computer designers or programmers or users for that matter is how errors arise and how they're controlled and how their effects are minimalized. And a lot of times you'll hear this as like defensive programming or as safeguarding, right? When we write programs that capture errors, right? Error handling, when we start talking about how to minimize their effects, how to, the program shouldn't just crash, how the computer actually maintains its state without effects to the user or with minimal effects to the user. The book has an excellent example. This one is used quite often in these types of courses when we talk about errors and an example of a problem with precision and accuracy in binary arithmetic. So this often arises with binary fractions. So a decimal integer can be exactly represented in binary from a given, if you have a sufficient number of bits for the representation, right, a sufficiently large enough range. In positional notation, the bits of a binary fraction, right, are the 0.1 to, which would equal like 0.5, 0.01, right? We can see that. Not all decimal fractions can be represented exactly in binary form, and it doesn't matter how many bits you use. And so they give an example here of this extremely long sequence here. No matter how many bits we use, we could not represent this 0.1 to the 10th in binary form. In 32 bits, we can only achieve a precision of 1 on 2 to the 32nd. So this is the example, right? The most documented failure of decimal to binary arithmetic is this Patriot missile story, which is a true story. The Patriot anti-missile intended to detonate release about 1,000 pellets in front of its target at a distance of 5 to 10 meters. Any further away and the chance of sufficient pellets being able to destroy the target is very low. So the Patriot missile's ground-based tracking radar detects and tracks the incoming target. The Patriot software uses 24-bit precision arithmetic. The system clock is updated every 0.1 of a second. The tracking accuracy is related to the absolute error of the accumulated time. So what that means is, as the software runs using a 24-bit clock, the error in the estimated position of the target gradually increases. This shouldn't be a problem because a Patriot battery was expected to be active for a relatively short period of time. So even though we knew this error was going to exist in this 24-bit precision on a 24-bit clock, you don't have a missile on for 24 hours. So the range of that error only accumulated with the amount of time that the battery was on, right, with the system on. And if the system is only designed to be on from basically the time you're ready to launch it until it achieves its target, it shouldn't have been an issue, right? However, in 1991, during the first Iraq War, the Patriot battery in Durand had been operating for over 100 hours. So they turned it on and then just left it there for a couple of days. During that time, that accumulated error on the clock had reached a significant number of seconds, right? 0.3433 seconds, which corresponds to an error, the estimation of the target position. So they calculated this out to be 667 meters. So in this case, the incoming Scud missile flying at Mach 5 was not intercepted. 28 U.S. soldiers were killed. Yeah, it's a great example because it's of course not possible to state that the missile would have been intercepted had the error not occurred, but it is possible to say that the error guaranteed that the system would fail. And so this is a pretty dramatic example of the consequences of failure to appreciate the effects of finite precision in binary arithmetic. The fact that these errors can exist is basically what we want programmers to understand and to help them either not design systems built around these kinds of errors or to understand the handling of precision to prevent these kinds of situations. So next we're going to talk about signed integers, and you've heard me use this term before, signed and unsigned data types. And signed integers really have to do with negative numbers and how we have learned to represent them. And really we've come up with 3 different techniques: sign and magnitude, 2's complement, and biased representation. And so each of these mechanisms has its own advantages and disadvantages. They're going to be something ultimately that as a software developer you cannot control because the language that you're using most likely has chosen its way that it's going to represent numbers, but a lot of languages then give you the opportunity to choose a signed versus unsigned version of that data type. So it's important to understand the differences so that you can make the correct choice for the operation that you're performing. So let's start with sign and magnitude representation. So an n-bit word has 2 to the n possible values. So we've hopefully established that. One way of representing a negative number is to take the most significant bit and reserve it to indicate the sign of the number. Because remember, when we talk about binary words, we're talking usually about 7 positions. We get 8 in a byte. And so by convention, 0 represents positive numbers, 1 represents negative numbers, which is probably one of the most infuriating things in computer science, is when we flip around the translation of 0 and 1 to represent positive and negative. You will find a lot of programming languages assign 0 to negative, 1 to positive, true or false. Boolean values in some programming languages will accept 0s and 1s, and you have to know which way it flips. So by convention, in binary, 0 is positive, 1 is negative, which I know for a lot of people is very confusing. Now, sign and magnitude representation of numbers is not used in integer arithmetic generally, as it requires separate adders and subtractors. There are other ways of representing negative numbers that remove the need for separate adders and subtractors. So you won't see this format very often. It's just good to know that it exists. So next we'll talk about 2's complement arithmetic. And this is what microprocessors use, right? This 2's complement system to represent signed integers because it allows us to perform subtraction by the addition of a complement, right? And that's where it comes from, 2's complement arithmetic. You can subtract 5 from 7 by adding the 2's complement of 5 to 7. And so if that seems desperately confusing, let's walk through this example a little bit. So starting with n equals 5, which, here, let me get my pointer out so we can follow along. If n equals 5, and we can see that 8-bit arithmetic binary representation of 5, the 2's complement is n, right, is 2 to the 8, which is this value right here, which equals this minus this, which gives us this, right? This string right here, and I'm not even going to try to read these out because I will get my 1s and 0s all over the place, represents this negative value, right? Negative 5, or a positive 123, depending only on whether I interpret this as a 2's complement integer or an unsigned integer, right? Because remember, with the unsigned integer, we assume a positive value. So take a look at this example down here. 8-bit 2's complement arithmetic. If we have positive 5, negative 5, positive 7, negative 7, right, here are our binary representations. And doing the same format where we learned how to add binary values, we get the 2's complement of 5. So let's back up for a second. Because we have several interrelated concepts all involved in this section. And if the math is a little fuzzy, you might have a little difficulty understand where we're going. A number and its complement add up to a constant. For example, in 9's complement arithmetic, a digit and its complement add up to 9. The complement of 2 is 7 because 2 plus 7 is 9. Are you following me? In our n-bit binary arithmetic, if p is a number, then its 2 complement is q, and p plus q equals 2 to the n. So in binary arithmetic, the 2's complement of a number is formed by inverting the bits and adding 1. So take a look at this example again. we have our 2's complement, right? If n equals 5, we have our binary representation, 8-bit arithmetic. The 2's complement of n is given by 2 to the 8. We see that binary value. And so we take our value minus our value, and we get this giant string of 1s with 1 0 in it. And this number right here represents our -5, right? This represents our -5. So let's look at this example. Hopefully this isn't too fuzzy. If we have our -7 to +5, so we have our 5, our -7, we do the addition, we get -2. This is our binary representation. The carry bit is the 0. Right, and hopefully you're following along, right? It's not magic, right? Not magic. 2's complement arithmetic is really just, we can think of it like this z equals x minus y, right? In our n-bit arithmetic, which we would do by adding the 2's complement of y to x. So the textbook has lots of examples to walk you through so that you can kind of really get a grasp on what we're doing here. And you can take a look at those either on this slide or in the textbook. So really, when we're calculating these 2's complement values, this system would not be so attractive if it weren't for the ease in which 2's complements can be formed. Right? If we consider the 2's complement of n, right, then we could walk through and arrange the expression 2 to n minus n by subtracting 1 from the 2 to the n and adding it to the result. So hopefully you can walk through these examples. I'm not going to make you do this. I know the math is a little fuzzy. But we need to understand, right? How do computers think about binary arithmetic? And so some properties of 2's complement numbers, right? The 2's complement system is a true complement system. So a positive x plus a negative x is going to equal 0. There's only one unique 0. The most significant bit, right, the one all the way on the left, of a 2's complement number is a sign bit. So the number is positive if the most significant bit is 0 and negative if it is 1. We have our range of an n-bit 2's complement number. And really the hardware for 2's complement addition and subtraction is the same because subtraction is performed by adding the complement. And that goes back to what I was talking about with why you don't see the sign and magnitude representation as much, because it requires separate adders and subtractors, right? When we think about in our processor, there's essentially two different places where this takes place, an adder and a subtractor. But with 2's complement arithmetic, we're always adding. We're never subtracting. We're just flipping the negative, right? Hopefully you see that. And that is why this is attractive, because it's easy to do and it requires much less work by the microprocessor. All right, to wrap up this section, we're going to talk about arithmetic overflow. So we talked about the range of our 2's complement numbers, and then we can start to think about what happens when we violate this rule by carrying out an operation whose result falls outside of this range of values that can be represented by 2's complement numbers. Because if this is how our computer does math, if we step out of that bounds, what's the computer going to do? So in this example here, our 5-bit representation, the range of valid signed numbers is -16 to +15. So let's look at our first case. So we have 5 and 7, right, which we can add together to get 12 in our normal math system. And if we walk through the binary math here, we should get 12 as well in this base 10. But take a look at case 2, our 12 and our 13. Right? We get a negative result because the sign bit is a 1. Right? We see that? The most significant digit is a 1. So if this answer was regarded as an unsigned binary number, it would be 25, which is the correct answer. But once the 2's complement system has chosen to represent signed numbers, it looks at that bit and sees -7. And that's a problem, right? Similarly, if we add together 2 negative numbers whose total is less than -16, we're going to go out of range. So we can take a look at this. We can add -9 with our representation and our -12. And while in our base 10 system we would get a -21, this is going to yield a positive result of 11. So these examples demonstrate our arithmetic overflow that occurs when we're using this format of 2's complement addition. If the result of adding 2 positive numbers yields a negative result, or if adding 2 negative numbers yields a positive result, that could be a problem, right? If we're outside of our range. If the sign bits for A and B are the same, but the sign bit of the result is different, then we can see that arithmetic overflow has occurred. So in practice, real systems will detect this overflow. We've developed ways to determine that this has happened from the carry bits into and out of the most significant bit of the adder. But we should understand how it's happening, and that arithmetic, I can't say this word today, overflow is a consequence of this 2's complement arithmetic and shouldn't be confused with the carry out, which is the carry bit generated by the addition of the 2 most significant bits of the numbers. And I mean, ultimately understanding how it's happening and why it's a problem is the goal here. So this is going to be the end of our Chapter 2, Part 2. In our next section, we're going to start getting into shifting operations for multiplication and division of our binary numbers and our computer arithmetic.